Okay, those are my announcements. Did that trigger any questions or anything for you all? Okay. So last time in class, you discussed ionic compounds with Roman numerals and the idea of having to use a Roman numeral to show the charge. And those are going to be used whenever we have something in the transition metals. So if the metal of our ionic compound is a transition metal, that's when we'll use the charge for it. So for example, if I have FeCl4, iron is a transition metal, so I want to show the charge of that because it can have multiple charges. So the name is going to be iron 4 chloride. Okay, and you did some examples of this. Remember that from last time? Yes. Okay. So we did that, and then you talked about polyatomic ions and the idea that groups of atoms act as one thing. What I wanted to point out here before moving on is the fact that with polyatomic ions, there are two of them I'm going to ask you to know. So there are hundreds of polyatomic ions in this world. There are two that I want you to know. I want you to know the NH4 plus, which is the ammonium ion, and the OH minus, which is the hydroxide ion. Those are the only two that I'm going to expect you to know from memory. Everything else will be directly given to you and so forth. Some other ones may enter into the homework, but I figure you can just search or look in the book or whatever for that information. But those two are the two that I'm going to want you to know for the exams. So if I was to write out putting these two things together, copper 2 hydroxide. On your paper, write out what the formula would be for copper 2 hydroxide. Okay, so copper 2 hydroxide, the 2 here means that the copper is 2 plus, so that's going to be Cu2 plus. Hydroxide is always OH minus. So the formula for these, or for this compound, is going to be CuOH, and you have to use parentheses 2. Right, parentheses 2. As a general rule in this course, I recommend students just put the polyatomic ions in parentheses, and just always leave them in parentheses, and you never have to worry about it. So if you have 2 of them, just put 2. If you have 1 of them, well, you just wrote extra parentheses, no big deal. Okay? So that would be the formula then for copper 2 hydroxide. Everyone good with that? Okay, so we did this, we talked about polyatomic ions and so forth, and we started talking about covalent bonds. So in covalent bonds, what is the primary difference between covalent and ionic bonding?
Ionic gives away the atoms,
Electrons?
electrons, and covalent shares electrons.
Exactly right. Okay? So they both fulfill the octet rule, but the primary difference is ionic gives that by the transferring of electrons. Some things give up electrons, some things take electrons. Where covalent fulfills the octet rule by sharing of electrons. Okay? Yeah?
Is it also the difference between them, like one uses bonding, another one uses the intermolecular forces to keep it together?
They are both bonding.
Okay.
Intermolecular forces occur between molecules. So if I have, we'll talk a little bit about this, but if I have water, for example, okay, I've got a water molecule here, H2O. And then I've got another water molecule here, and another water molecule here. These lines are covalent bonds, and those are covalent bonds. Now, an intermolecular bond is an interaction between one molecule and another molecule. So it's between molecules. So here's one, here's one, here's one, here's one, here's one. So when you've got these individual molecules, the bonding inside the molecules is covalent, but the bonding between molecules is intermolecular. Okay? The way I keep track of this, and I don't know why I even know this, an interstate crosses state lines. Okay, it goes between various states. Intra would stay within a state, and that would be like your covalent and ionic. So intermolecular forces are the ones that go between molecules.
And those can vary in strength?
Yes. Yeah. We'll talk a little bit about them. This that I've drawn here is the highest strength intermolecular force. It's called hydrogen bonding. But there's several other ones that can go on. And they do have important properties. For example, water should have a boiling point. If you just look at the elements that make up water and their ratios, water should have a boiling point probably around 20 degrees Celsius, which would be room temperature, and the world would not exist as it does. But because of the hydrogen bonding here, they stick together extra, and that moves the boiling point up to 100 degrees. So it doesn't sound like a lot of interaction when we're talking about it, but it does become really, really important in terms of setting properties. And we'll talk a little bit about those types of things, but we first have to finish up covalent and then talk about shapes, because shapes plays a big part in it as well. Yeah.
So that was the intermolecular?
Intermolecular, yep. Intermolecular, or between molecules. This example that I've got drawn is called hydrogen bonding. And let's say, for example, ionic and covalent has a strength, like the amount they stick together is 1,000. Hydrogen bonding would be like 100 or 50. So an order of magnitude less strong than what we actually see inside of a molecule or a compound. But they do play an important part in some aspects. They're really kind of hard to understand though, so I'm not going to discuss them too much. Okay. So that's the difference between ionic and covalent, is this transfer of electron or sharing. The other way that you can remember it easily is that ionic compounds are between a metal and a nonmetal, and a covalent compound is between two nonmetals. Dr. Russell said she did some examples of this with you. So you guys buying that? You're okay with that? Okay, good. So we're going to continue on talking about how to explain covalent compounds using dot diagrams. And I don't know the exact examples that you guys used to draw out these molecules and so forth last time. I'm going to assume did you do water? Basic ones. Yeah, no. You did water, carbon and 4 chlorines or something like that, probably. Okay, so let's try something a little more difficult. If you're having a big problem with it, let me know. So let's do NOCl. NOCl. See if you can draw out what the dot diagram would look like for the compound NOCl. And I'll give you a little bit of time and then we'll walk through it. let's say 30 seconds or so. Everyone have their ideas? Okay. So I'm going to walk through it how I would do it. I don't know exactly how she explains it, but this is the way I go about doing it. So first off, I need to figure out which element is going to be in the center of my molecule. Okay, so which one are going to have things bound to it? And I've got three options here, nitrogen, oxygen, chlorine, but I can throw out chlorine right away because it's a halogen. Halogens only form one bond, so they can't be in the middle. They can't form a bond on either side because that would be two bonds. It just doesn't happen. So you can throw out halogens from being in the center, and you can also throw out hydrogen from being in the center for the same reason. So that's not going to work, leaving nitrogen and oxygen. And then generally, I choose whichever one is furthest to the left on the periodic table as my center point to start with. So this time, nitrogen is further to the left, so I'm going to draw an N. And then put my 5 dots around the nitrogen. So there we are. Next up is my oxygen. I know the chlorine is going to be on the outside and form one bond, so I'm going to save that for last. I'm going to put my oxygen here, and I'm going to put 1, 2, 3, 4, 5, 6 dots around that. So I have two options. I can put, well, let's do this first. I'm going to form a bond here between these two. So now my oxygen has 1, 2, 3, 4, 5, 6, 7 dots around it. My nitrogen has 1, 2, 3, 4, 5, 6. So where does the chlorine go? It could sit off the oxygen here, which would fulfill the octet for oxygen and give it 8. But that doesn't help with my nitrogen. That's not going to help because my nitrogen won't pick up enough electrons. So the other option is to put it on the nitrogen here. 1, 2, 3, 4, 5, 6, 7. Giving it 8 around the chlorine. Now my nitrogen is 1, 2, 3, 4, 5, 6, 7. And the oxygen is 1, 2, 3, 4, 5, 6, 7. So nitrogen and oxygen both have 7. So what is it going to do to fulfill the octet then?
They're going to bond together.
Yep. It's going to form another bond. As a matter of fact, this one, I could have drawn a little better. That one and that one are going to form another bonding pair. So redrawing this a little bit nicer, I'm going to have my nitrogen, and it's going to form a double bond to the oxygen. And then on the other side, or it doesn't really matter what direction it is, on one of the other sides, I'm going to end up with my chlorine. So looking at this now, I have 2, 4, 6, 8 on the oxygen, 2, 4, 6, 8 on the nitrogen, 2, 4, 6, 8 on the chlorine. This is the only arrangement you can do that has 8 around everything. No matter what other types of arrangements you come up with, you're not going to have it. You have more or less. So since everything has 8, that's a good dot diagram. Does that make sense? No? Okay. Let's try another one. Let's do CO2. Unless, well, I guess if we do examples you guys did last time, let me know. But
Yeah, we did that one.
you did
last
CO2?
time. Yeah.
Okay. Let's do CO Br2. And again, this is another one that I would consider a level above the basic ones. It's It's not the hardest in the world by any means, but it's definitely a step up. So. If you guys get the first one, there's a really tough one over on the other board for you. SINOH. That would probably be considered unfair for the exam. Okay, let's say 30 seconds or so for COBR2. Okay. COBR2. Any questions first? No? Okay, so I'm going to put the carbon in the center using the same logic I did before. Place 4 electrons around the carbon because it's in the 4th column of the periodic table.
Wait, why did you place it in the center again?
Okay, I placed it in the center. Bromine I'm not going to place in the center because it's a halogen, so that's out. And then looking at it, carbon is further to the left on the periodic table, so I'm going to put that in the center, whichever one's further to the left.
Oh,
The reasoning behind that is because it's going to make the most bonds. It needs to make 4 where oxygen needs to make 2,
okay,
but I just remember as the furthest to the left.
okay.
And that's not always going to work out 100%, but 90, 95% of the time it does. Okay, so we'll make an oxygen here, or place an oxygen here. 1, 2, 3, 4, 5, 6, around that. And then to do things slightly different, I'm just going to put a bromine. Okay, here. 1, 2, 3, 4, 5, 6, 7. So the bromine has its filled octet. Oxygen is still missing 1, but the carbon is still missing 2 there. I have another bromine to place, which is helpful. But with this type of arrangement, I need to form a double bond here, and then put a bromine on this side. And that's going to fulfill my octet. So if I redraw this, I wish there was a quick way to redraw it. But there you go, redrawn. You've got a double bond here, a single bond there, and a single bond there. Giving us 8 around the carbon, 8 around the oxygen, 8 around the bromine, 8 around the bromine. You guys ever do those Sudoku puzzles or whatever they're called? I've got some friends who love those things, and they drive me nuts. But I think about these types of problems in the same way. You've got a basic rule. The basic rule is you need to arrange everything to fulfill the octet. And then it's just a matter of going at it and trying the different combinations, putting things in different places until it falls true. Just like in the Sudokus, when they do them, they always do them in pencil so they can erase when they make mistakes and try other things. The same thing here. You just start working on it, and if you can't figure it out, try again with something else. Okay, just fulfill that basic rule there. Okay, so that's the dot diagram for this one. Questions about that? This really is one of those examples in class where practice helps a lot, because you kind of catch yourself making wrong mistakes and can correct for them early. You're not spending 5 minutes trying to draw out the dot diagram or something. If you're spending 5 minutes to draw out dot diagrams, you're never going to get through the exam that we've got, just because of the time constraints and so forth. So I would highly, highly encourage you to practice these in whatever way you find best. Oh, the other one, just for completeness, if you tried it out, you've got a triple bond to the end. 1, 2, 3, 4, 5. And then you have a single bond to an oxygen. 1, 2, 3, 4, 5, 6. And then a single bond to the hydrogen. Yeah.
I had mine opposite. I had like a double bond between Si and oxygen, and then a double bond between Si and nitrogen, and then a single bond with hydrogen and nitrogen.
Okay.
So why does the hydrogen have?
Okay. Well, why doesn't hydrogen have 8?
Yeah.
Because the first orbit only takes 2 to fill.
Oh.
So hydrogen takes 2. That's the one exception to the 8. Okay. Now going back to the previous thing, because I think it's a good point to make here. N, and you see you had a double bond to the end,
Yes.
and then what did you have around it?
And then I had a bond to the hydrogen from the nitrogen.
Okay. So hydrogen, and then 2 more, right? And then on the other side you had the oxygen. 2, 3, 4, 5, 6. Two, 4, 6. Well, SI's got 1, 2, 3, 4, 5, 6, 7, 8. I think it works.
Would it work either way?
Yeah, I think it's either way. It'd be fine. I said we had to do something stupid. 5 nitrogens. Yeah, I think it works.
Is that possible for like a lot of different
No. Just when you get to the more and more complex ones, you sometimes pick up a second possibility.
Okay.
2, 2, 4. Yeah, that's fine. That will work. Okay, so either one of those would be accepted in that case then. Okay. Do you guys feel like you've got a grasp on dot diagrams for covalent? Yeah. Okay, so now we're going to move on to something a tad bit easier, and this is naming of the covalent compounds. Now for this class, you are only going to be naming binary compounds, so ones that are made up of 2 elements. So this SiNOH, we will never name that. COBr2, we're not going to name that either. So let's get rid of those. The types of things we're going to be naming: CO2, H2O, two elements, SiF4 and P, let's do N, C, actually let's do N2 Cl4. Okay, so all of these then have two elements in them. And because they have two elements in them, they're called binary. So naming of binary things. Now, when we go to name these, the first two rules should look very familiar. They're the same as naming of ionic compounds. So the first element in each of them is going to stay the same. So here, this is going to be carbon. Over here on this one, it's going to be hydrogen. Over here, it's going to be silicon. And over here, it's going to be nitrogen. Then, the second element's name is going to change the ending to an IDE. So this is going to be carbon. And this oxygen is going to change to oxide. Same thing here. This is going to be fluoride. And finally, chloride. So these are same two rules as ionic compounds. The difference between them, between ionic and covalent, comes in the third step, the fact that there is a third step. For covalent compounds, you need to show how many of each element there is. And to do this, we use prefixes. So I know you're not going to be happy about this, but I want you to learn the prefixes here. You don't really have to know 7, but I put it in there anyway because it seems silly to leave it out. The prefix for 1 is mono, prefix for 2 is di, and then you actually get into the shape. So how many shapes are on a triangle? 3. Okay. A tetragon, does anyone know what another name for a tetragon is? It's a square. It's a fancy word for a square. So that's 4. A pentagon is 5. Hexagon is 6. Octagon is 8. So octa is 8. Hexa is 6. Penta is 5. Tetra is 4. Tri is 3. And then di is 2. And mono is 1. So mono, di, tri, tetra, penta, hexa, octa. You'll pick it up pretty quick, I think. So over here then, for CO2, we need to show how many we have for each of them. So for the carbon, we have 1 of them. So that's going to be mono. And the oxygen, we've got 2. So that becomes di. So one perfectly acceptable name for this class is monocarbon dioxide. Normally, chemists leave mono off the first one, but never the second one. So as chemists would speak, we would say carbon dioxide. And you guys have all heard of carbon dioxide before. It's the air we exhale. But if in this class you want to call it monocarbon dioxide, I'm perfectly fine with that. It doesn't matter to me at all. For your lab, you may want to check with your lab instructor if they care or not. But I don't care at all for the course, the lecture itself. So just put the prefix there. Okay, so for hydrogen here, the name of H2O, according to the proper naming of chemistry, is dihydrogen monoxide. Dihydrogen monoxide. Di meaning 2, mono meaning 1. I dropped an O because we don't put 2 O's together, but if you did it, I don't care. Dihydrogen monoxide. Okay, otherwise known as water. Okay. Does that make sense? Okay. Over here, SiF4 would be silicon. tetrafluoride. And the last one is going to be dinitrogen tetrachloride. Dinitrogen tetrachloride. And this is really how we name things in real life. If you go to food or something and look at the ingredients list, you're going to see that if it has a covalent compound in it, it's going to be named this way. And this is not uncommon to see these types of things in ingredients lists and so forth. Think you got a grasp of it? Let's try a couple of them. Let's do N4, F8. We're just making that compound up, but N4, F8. Okay. Anyone want to share what they got for it?
Tetranitrogen.
Tetranitrogen.
Octafluoride. Yeah, fluoride.
Correct. Yep, you're exactly right. Tetranitrogen octafluoride. Yeah, I try and come up with more complex things, but it's really just that. You have a problem seeing? Yeah, I can see it all. Okay. Should we try one more? I guess I don't. Let's do P3S. P3S. P is phosphorus. Now I'm a little nervous about spelling it. S is sulfur. Okay, P3S, this one is going to be tri-phosphorus monosulfide.
You said, or you could just go sulfide.
No, you have to use mono in this case because it's the second one. Okay, you always use mono on the second element. And that's one of the reasons why I say just always use it, even on the first, because I won't count it wrong by any means. And then you don't really have to worry about that. Triphosphorus monosulfide. Yeah, I got nothing else there. You guys got any questions about that? That's really all there is to it. Now, going the other direction is much, much easier than in ionic compounds because you don't have to worry about balancing charges. So if I was to write out dioxygen tetrachloride, you probably can very quickly go to the formula for that. Because it's simply O2 Cl4. O2 Cl4. You don't have to worry about balancing charges or anything along those lines. It's just a matter of writing down the elements and then the number of them. One other thing I should mention is that you are not ever going to be asked to predict the formula for a covalent compound. So like in ionic compounds, I said what compound would form between calcium and chloride, and you can look at the charges and figure out what that compound would be. That doesn't work for a covalent. So for covalent compounds, I'll either have to tell you the name directly or the formula directly. I won't be able to say, take phosphorus and sulfur and predict what compound forms there. It just doesn't work the same way. So you don't have to worry about that at all. Questions about naming? Usually students like covalent naming. It's pretty straightforward. The other thing I want to point out here is, if you look, we always use a prefix on the second element. Okay? So if you see a prefix, one of these prefixes in the name, you know immediately it's a covalent compound, because that's the only time we use them. So if you see a prefix, it is covalent. If you don't see any prefixes, then it's not covalent. It's going to be ionic for you. Okay, so let's try something slightly different. Would be the type of question you might see on an exam. So on the exam, generally what I do for this is I say, name the following compounds, and I give a list of compounds, and then you name them. So let's try that. Let's say that we have NO2, stick with things you guys would know. LiOH, KCl, and Si3. So for these four compounds, let's take a minute or two. Sorry for writing too low. And see if we can name what they are. Okay. NO2, LiOH, KCl, and Si3. Play with these lights just a little bit. Is that better? Yeah? Okay. Let's say another 20, 30 seconds.
What is
I is iodine. Sorry. Remember, on the actual exam, you will have a periodic table that has the names of the elements for you. So don't forget about it when it comes time. I completely recognize you don't have that now. Okay. Everyone have their ideas? Okay. What do we have for NO2?
Nitrogen dioxide.
Nitrogen dioxide. Does everyone agree with that? Okay. Nitrogen dioxide. And that's absolutely correct. Nitrogen is a nonmetal, oxygen's a nonmetal, so it's going to be covalent, which means we have to use the prefix here. And putting everything together then, nitrogen dioxide. Perfect. Okay, LiOH.
Lithium monohydroxide.
Lithium monohydroxide.
I just have lithium hydroxide.
Okay. So in this case, this is a polyatomic ion, and this is a metal. So we have a metal and an ion reacting. Well, basically, that's giving it away. This is going to be an ionic bond. So anytime you have a polyatomic ion, that's going to form an ionic bond. So the name of this one is going to be lithium hydroxide. Lithium hydroxide. Okay, the next one, KCl, is that going to be ionic or covalent? Ionic, right? It's a metal and a nonmetal. And the name of this one is going to be potassium chloride. Potassium chloride. The final one is Si3. What do we got for Si3?
Silicon trioxide. Wait, no, triodide.
Okay, pronouncing it's probably the hardest part. However, it is S, so it's sulfur, because Si is silicon. Not the intent of the question, but so this part here is just sulfur. And then it's going to be I don't know, iodide. That's what I'll go with. Triiodide. But I completely understand how the silicon came in.
I thought you said S-I.
Yeah, when you said SI, I didn't look at the monitor, I wrote it down, and I didn't realize it was a
SI.
capital I.
Going back to one of our very first lectures, why it's important that we capitalize and not capitalize. But, yep, S-I. Okay. Everyone feel comfortable with that? Yeah, okay. Yeah.
Will there be, or where would you recommend some practicing for the molecular compounds with the covalent compounds with making sure they all equal?
So the dot diagram
Yeah.
practice? Okay, so dot diagrams are one of the things high school teachers harp on for hours and hours. I'm not exactly sure why. And they have a lot of examples and so forth online. So if you go and just type in dot diagram practice, you will have hundreds and hundreds of PDFs that you can look at, coming from high schools and so forth. Now, I will happily check them over and so on. Also on the CK12 site, they've got examples for you to practice that you can go through and practice as well. If you want, I can happily too come up with a worksheet. Why don't I do that, then I've got it. A worksheet of dot diagrams for both ionic and covalent compounds, like maybe 6 of each, and then the key with it. So my idea is I'll have one page that's just the problems, and then a separate page that's the key, so that you can do the problems first and then look for the answer.
How many of those would you think that we would have on
In terms of actual dot diagrams, you'd probably do 6 maybe on an exam, but some of them are going to be parts of other questions. So as you see in this chapter, everything builds upon itself. You start with a dot, like the Lewis dot structure, then you go into is it ionic or covalent, then from that you go to the dot diagrams, and then from the dot diagrams you go to naming, and also from the dot diagrams you can go to shapes, and then further on to other So I always have a long question that we'll do some practice of, but one part of that is a dot diagram too. So there we are. Okay, other questions? And also, when we do dot diagrams on the exams and so forth, I'm not going to pick the super hard ones by any means. There may be one hard one and 4 easy, like water, those types, just because I want you guys to show that you understand the basics of it, but not spend a lot of time doing it. I don't want an exam, like half of your exam being drawing dot diagrams. Yeah, so we already did all that. I think we're good there. Now, as you are aware, water, for example, we don't use the proper name of water except probably in jokes. That's the only time I've ever seen the true IUPAC name. IUPAC is what we call the naming that we're learning here. But oftentimes, for a lot of different compounds, there are common names as well. These likely existed before the IUPAC conventions. So water was called water long before we came up with a way to describe it as dihydrogen monoxide. And there are some other examples here. You guys don't need to know any common ones at all, but I just want you to be aware that sometimes some common names aren't the true official names according to the chemistry journal. Laughing gas is N2O, nitrous oxide. Well, the proper name would be dinitrogen monoxide, just like water and so forth, as we go through it. So we do see these types of things. And largely it's because the names were around long before the rules. So we just stick with them. If you know a common name for something, like for example, NO2, if you knew the common name for NO2 and you wrote that down, I would accept that. However, I'm not sure any of you would know the common name for NO2. I'm not even sure what the common name of NO2 is. Okay, finally, there is another class of naming, and you guys are not going to be asked to do this on the exam or anything, but I just want to introduce it to you. This is a naming used only for organic compounds. So those would be carbon and hydrogen, and then a few other things. A little bit of oxygen mixed in, a little bit of nitrogen mixed in, and so forth. Organic gets very, very complex in terms of their compounds because you can have 1 carbon, 2 carbons, a billion carbons, it doesn't really matter. So you need to be a little bit more involved in your actual naming of them and so forth. And because of that, there is a different set for organic compounds. So CH4 is methane, CH3OH is methanol. So if you look at this OH right here replaces a hydrogen, and because it does that, you change the ending to an OL. So there are systematic rules that go with the organic naming. Here, you go from CH4 to C2H6. You've added another carbon, so the beginning isn't meth. It then starts with F. And if you go through organics, it's meth, eth, prop, but, pent, so forth, oct, and so forth. So it does follow similar rules. We're just not going to take the time to learn them in any way, shape, or form. One important one that is in everyday life from the organic is octanol. Octanol is basically what you're buying in the gasoline. You buy gasoline. That's what your car uses to run and so forth. Octanol. And octanol is C8H18 is what it is. I don't care that you guys particularly know that, but that's what it is. So you start out with simple names and then it gets more complex. Glucose, sucrose, C6H12O6, C12H22O11 here. These are sugars. So different types of sugars have different formulas, and because of that, they have different names, and it goes into a whole other type of convention for you. So when you see things like methanol, ethanol, propanol, What are grills these days? They're propane?
Propane.
Propane grills. That's an organic name. Prop is for 3, meaning it has 3 carbons. Butane, which are butane lighters, but is 4. It means that there are 4 carbons in that fuel. They're all different types of organic compounds we burn. It's very, very common to burn organic compounds for energy. Ethanol, it's not really what we burn, it's what we drink. Okay, that's what makes alcoholic drinks alcoholic, is ethanol, by the way. But now that I say that, I do want to say this. Do not go to the store and buy ethanol from the shelf, because you can go to like a pharmacy and buy ethanol for cleaning wounds. That is not to drink. That is, they specifically poison that so that you can't drink it. If you really, really want, well, you can't buy pure ethanol to drink. I can buy it because I'm a chemist, but generally you can't. This is silly. What, does anyone know what the highest content alcohol is you can buy? I know. I knew when I was a kid, but that's just part of me growing up. What? You can guess. I'm not going to think less of you if you know.
It's like Everclear.
Everclear is the highest alcohol you can buy. In this area, the highest you can buy is 190 proof, which is 95% ethanol, 5% water. In Iowa, where I grew up, you can actually buy 198 or 198 proof, which is 99% alcohol, 1% water. It's outlawed in most states, though. When I was a kid, not a kid, when I was a young adult, I had partaken in Everclear a few times. Okay, so I know of what I speak. However, be forewarned. It's disgusting. Let's just go with that. It's just utterly disgusting. It's not worth it by any means. Yeah, one time in class we had a huge discussion about moonshine. For like 2 days we talked about moonshine. One of the students' family made moonshine, and he was really interested in it and wanted to talk about it, so we talked about it. Perfectly fine. My grandfather actually used to run whiskey from Iowa to Chicago, and there's a brand of whiskey called Templeton Rye, and it was Al Capone's favorite, and Templeton is where my grandfather's from. That's the type of whiskey he used to run. So you can go to the farm, and actually he's got a car out back in the farm that's got bullet holes in the side from one of their deliveries that went wrong in Chicago back in the day.
I have a question.
Yeah.
Moonshine, because I know like when a lot of people talk about moonshine, they talk about like how strong it is,
Mhm.
and like,
Yep.
what proof is that? Because when I think of moonshine, I think of like pure alcohol too, because everybody talks about how strong it is and how dangerous it is, because it's
Yeah.
so like,
Well, generally what they do is they'll make the moonshine and then they'll dilute it down to something that's actually drinkable. If, for example, you go down to the distilleries downstate and you look at what they do, they actually take and make their alcohol at about 150 proof, so 75% alcohol, and they call it white lightning, is that form of it, and then they dilute it down to something else. So most moonshine that you buy is probably, I would guess around 120 proof, somewhere around there. But if you make it yourself or your family makes it themselves, you can pretty much control how strong or how weak you want that to be. But don't just go out and start trying to make moonshine, by the way. It's not something, yeah.
Any corn using that, like how that breaks down, or?
You can use corn. You can use several different things.
So is that like the sugars?
The sugars, the fermenting of it and so forth, yep. There's a lot to it, so that's why I'm saying don't just go out and make some. Don't make
So it's
bad.
made out of corn?
You can make it out of corn. That's what they make it out of in Iowa, actually, 'cause they got a lot of corn.
So how does the ethanol that we're talking about right now differ from ethanol fuel?
Very, very little,
Okay.
actually. Ethanol fuel you burn, you light and burn, and actually when you drink ethanol, you break it down to energy inside your body. So there's really, I mean, procedurally there's some differences in terms of purity and making sure it's safe and things like that. but the actual chemical itself is exactly the same. Yeah.
This might be a really silly question. So what would happen if you put alcohol in your car, like drinking alcohol in your car?
Well, if
Since
you
it's not like a really big difference, even though it's
You
adding
could.
water to it.
you could absolutely put ethanol in your car, but no car runs, well, I shouldn't say no car. No car I know of or ever seen runs on pure ethanol. They're usually mixtures. I think there are actually.
Ethanol is actually being used as race gas.
Yep.
For a lot of pro race teams, IndyCar and NASCAR both use ethanol. And a lot of grassroots racers are switching to using ethanol. It just requires a different ECU flash and injectors. I know a lot of
Your
racers
engine
run
needs to be
ethanol.
timed differently and so forth, I know. But ethanol is going to inherently pack less power per volume. I'm not sure why they would
That's why I was
use
asking,
it.
because I don't know if it's pure ethanol or if it's a mix of some sort.
Yeah, they may be, yeah, I don't know. I don't know enough about racing. I got a friend I could ask, but I'd have to reach out to him. So, yeah, but that's ethanol. Ethanol has actually got a lot of different uses. Now, growing up in Iowa, I know them, because it's a huge ethanol producing state from the corn and so forth. But that's the way it works. Okay, so there is that. Let's see, what's next? Multiple bonds, we talked about that, we've done that. You know, you can have one covalent bond to fulfill a octet 2 or 3. You can even have 4 in very limited situations. This came through on the slide here without my intent. You notice this dash? That dash is 2 bonding electrons. So, for example, right here, I could show these 4 electrons as 2 dashes. And that's the way chemists do it. It's just easier to draw. So if I have carbon, and then let's say CLs. Actually, let's make my life easier. And not do CLs, but do H's. H's like this on each side. I could redraw this as just a C and then dashes to the H's. They're completely interchangeable there. Normally in class, I'll draw the electrons because I think it shows the electrons a little bit better and so forth when we're discussing things. But you can go ahead and put the dashes in if you're familiar with it or comfortable with it, whatever you want to do. I can switch between them. But a dash is 2 electrons that are bonding. That's the way it goes through. Good with that?
So if you were bonding, if you had a double bond, you put 2 dashes next to it.
Yep. Yeah, so CO2, for example. Let's see. Like that. All right. It's carbon with 2 double bonds to the oxygens. It's just a convention. It's actually, the reason it is because chemists are lazy, and it's easier to draw that than to draw all the dots. So that's the idea there. And that brings us to shape. However, I think that's where we're going to end today because of the fact that shape is going to take us quite a bit of time to go over.